So yeah, don't use the solution stoichiometry thing because it will fail you when you most need it. All right, another example. This was intended to be an exercise, but we'll do it together. We have a 25 milliliter sample of HNO3, that's nitric acid. And that requires 35.7 milliliters of this concentration of BaOH2, barium hydroxide, to, keywords, completely react with all of the HNO3 in the solution. We want to know what the concentration is for that HNO3 solution. A couple of things that we need. We need to know what we're looking for. I underlined it in fuchsia so you can find it. We're finding concentration of nitric acid. What are our units for concentration? Capital M molarity or molar. And what is that equal to?
Mole over L.
Yeah, capital M equals MOL over L, big L. So moles per liter. You can use this like a density equation. So you can find whatever you're looking for, any of these three variables if you have the other two. Or you can use this to turn capital M into moles over liters. That's how I prefer to do it. You're welcome to do it either way. So we're trying to find molarity of HNO3. That means that we need two pieces of information about the HNO3. We need the moles, and we also need the liters. We have the liters. We do not have the moles. We'll have to get the moles from somewhere. We were given two pieces of information about our barium hydroxide, an indication that we can probably start there. So this 35.7 milliliters. Milliliters is 1 unit. Molarity is secretly 2 units. So I'm going to start with 35.7 milliliters for this calculation. How do we use milliliters and molarity with each other to get something useful? We can convert it to liters. We don't actually have to. If we had it in liters, how would we use liters and molarity together to get something useful? We can get moles. So if we have liters, and we have molarity, liters times molarity, if we wanted to rearrange this, liters times molarity equals moles. Or if we rewrote our molarity as moles over liters, that would look like this. Moles over liters, the liters will cancel. So that'll get us moles, but what I did here intentionally is I didn't get rid of that milli. You can always get rid of the milli and bring it back later if you want to, or you can just choose to not get rid of it and carry it through. In this case, it works to carry it through, and I'll show you why in a bit. So what we're getting out here is, let me put that in red, millimoles, BaOH2. .7 times our concentration, 5.38 ... millimoles of barium hydroxide. Now we've got something in moles. We've got a chemical in moles, but we need to get this different chemical in moles, nitric acid in moles. How do we convert between two different chemicals? What do we need to do that? Ratio. We need a ratio that is between barium hydroxide and HNO3. The ratio we would get from a balanced equation for an acid-base neutralization reaction like we have here? Have we talked about those before? Nobody knows. Great. HNO3 is an acid. We know it's an acid because of what? The H in front. Barium hydroxide is a base. It has the OH groups in there. Those will pop off in solution to form OH minus. The H pluses and the OH minuses will react. We have two OH minuses that will be produced by each of the barium hydroxides. So we need two H pluses from our nitric acid to get those to react. The products in this case don't matter because we just care about the ratio of these two things. So it's a 2-to-1 ratio. So starting with that, or picking up rather, with that 5.38 ... millimoles barium hydroxide, BaOH2, we will need 2 HNO3s for every 1 barium hydroxide. So we end up multiplying by 2. This is one of those cases where if you use the M1V1 equals M2V2, you get it wrong. Because it doesn't take into account this 2. So this gives us millimoles of HNO3. How can we use moles to get to molarity?
Divide it by liters.
Yeah, divide it by liters. And in this case, since I left that milli on there, we can just divide by 25 milliliters. The millis cancel out, and the moles over liters turns into molarity. So the concentration of our nitric acid is 0.431 molar. Again, you're welcome to get rid of the millis first and then work with it from there. It doesn't make a difference. Mathematically, it's equivalent. I just chose not to do it because I know that I can do it without getting rid of the millis, and I know that some of you probably can also do it without getting rid of the millis. So I wanted to show you that as a trick. Questions? Okay. Acid-base titration. This is what we're doing in lab this week. This is also what we'll be doing in the lab practical next week. In a titration, we can determine the concentration of an unknown solution. To start, a substance in a solution of known concentration is reacted with another substance in a solution of unknown concentration. So that previous problem that we just worked on, that's the same sort of calculation we would do for this step. If we have, for example, hydrochloric acid, one of the acids we'll be using today, and sodium hydroxide, the base that we'll be using today, the net ionic equation for that reaction, so just the things that participate, is H plus OH minus goes to form H2O. And it's a 1-to-1 ratio. Let's represent our HCl solution by this diagram where we've just got H pluses represented in solution. We'll also be using some OH minus, and we've got that loaded into our burette. Our burette lets us accurately add, or accurately measure the amount of solution that we add into our acid. So we got base in our burette and acid in our Erlenmeyer flask. Initially, we have no base only acid in our Erlenmeyer flask. As we add in some of our solution, you can see the solution level dropping. We add some of that in, and it reacts. The sodium hydroxide that we're adding in reacts and forms H2O. And we have an indicator in here that reacts with base. So if we have a little bit of excess base, it reacts with the indicator and it turns this fuchsia pink color. So once we hit the point where we've got equal amounts of base and acid, it's all water. We don't have any extra stuff. We'll have some salt in there, but we don't have any extra important things in there. And then if we add just the tiniest little bit of that sodium hydroxide, it reacts with the indicator to let us know, hey, we're at about the equivalence point. We've got equal amounts of acid and base. It's completely neutralized to form water. So the equivalence point is the point where our H plus and our OH minus are equal. All the acid and base have reacted to form water. Questions? So we'll be doing this. You could drink it. If you didn't have an indicator in there, I would say, yeah, probably. Sodium hydroxide and HCl will react to form salt water. So you could drink it. You shouldn't. If you do it at home, that's on you. All right, so the equivalence point is usually signaled by an indicator. The indicator that we're using is phenolphthalein. This will be on our spelling test. Oh wait, we don't have a spelling test, so you don't have to know how to spell it. Phenolphthalein. It's clear in acidic solution. This is part of the reason why we have the acid with the indicator, because if you put it in the base, then it'll just always be pink. So it's clear in acid, pink/fuchsia in base. And there doesn't have to be much. It's a very strong indicator. So even though we're only using a couple drops of 0.1% phenolphthalein, it's really bright, and it comes across well. Typically, we're going to know the concentration of one reactant solution. So for our lab, we're going to measure out some of the solid acid. We know the molar mass and the identity of that acid, so we know how many moles of acid we've added into our Erlenmeyer flask. Then, because we know the chemical identity and we know the sodium hydroxide, we can figure out how much sodium hydroxide we added to figure out the concentration of our sodium hydroxide solution. Then we can take that and figure out the concentration of a different liquid acid solution. All right, so sodium hydroxide, this would be the second step. It'd be added to an HCl solution. When they reach stoichiometric proportions, the equivalence point, the indicator changes to pink. Our goal in the lab is to get a light pink color. This is a little bit on the light side of light pink. There's some luck involved in getting a solution that's that light pink of a color. If you hit this dark pink endpoint, that means you've overshot it. Sometimes that can be as little as half a drop to go from no color to too much. If it's just about, if you just add one drop and it does that, that's fine. The goal is we want to be within a couple of drops. We're not getting paid millions of dollars to do this titration. If we were, we would get it perfect every single time. We'd stay in the lab for weeks on end trying to get the perfect light pink endpoint. If we were getting paid millions of dollars, you're not getting paid anything to do this. just knowledge and experience. So I'm not going to be too much of a stickler about making sure that you get a light pink endpoint every single time. Let's say that we use calcium hydroxide. What mass of calcium hydroxide is present in a sample if we titrate it to its endpoint, its equivalence point, with this many milliliters of this concentration of nitric acid? And you're given a balanced chemical equation. Where do we want to start on this problem? What should be our first number? Yeah, 44.02 milliliters. In solution stoichiometry, liters is kind of like grams for the stoichiometry stuff that we've done before. So we're going to start with milliliters, and we can convert that to liters by dividing by 1,000. So that many liters. And just move the decimal place over 3 times. How can we use this liters? Yeah, multiply it by the molarity, since molarity is secretly moles over liters. That will cause our liters to cancel, and we'll be left with moles. So our liters cancel, and this is the number of moles of nitric acid that we used, that we get out of here. That's how many moles of nitric acid we used. We've kind of exhausted what we can do with nitric acid. What's the thing that we care about? What's the chemical we care about here? CaOH2, which is called what? Calcium hydroxide. Yeah. So if we want to get to calcium hydroxide, what do we need to use? Yes, we need to use the ratio. And our ratio here is 2 to 1. We need to use 2 nitric acids, 2 HNO3s. That goes on the bottom so that the units cancel. And the calcium hydroxide goes on the top. Since we have 2 hydroxides in a calcium hydroxide, we only need to use 1 to produce 2 hydroxides. So we need twice as many nitric acids to react with it. So this will give us the moles of calcium hydroxide, and we want mass. How do we go from moles to mass? Molar mass. So we'll have to calculate our molar mass. So multiplying by our molar mass, you should know how to calculate molar mass. We get 0.144 grams calcium hydroxide. you'll be doing this calculation backwards, sort of, in the titration lab. Questions about this example? All right, one for you to try. What mass of oxalic acid, H2C2O4, is present in a sample if it is titrated to its equivalence point with that volume of that concentration of sodium hydroxide? You are given the balanced chemical equation. I highly suggest that you try this one. All right, oxalic acid has two H's in front. That means it's diprotic. It produces two H pluses when you dissolve it in water, or at least it can. That's why we have a 1:2 ratio in our balanced equation. We are looking for the mass of the oxalic acid. The titrated to its equivalence point part is just letting us know that we've got equal amounts of moles of H2 or H plus and OH minus, so we have to use the ratio. That's all that's telling us. We're starting with milliliters and molarity of sodium hydroxide. So starting with the milliliters, we can convert that to liters. We can multiply that by our concentration. This will give us moles of sodium hydroxide. From that number of moles of sodium hydroxide, we can then use our ratio from our balanced equation. Our ratio is 2 to 1. We need to use 2 sodium hydroxides to fully react with each oxalic acid. So 2 NaOH on the bottom, 1 H2C2O4 on the top. And now our units, if we calculated here, would be moles of oxalic acid. Since we're trying to get to mass, we need to use the molar mass of oxalic acid. Which is 90.034. Grams over moles. And that'll give us the grams of oxalic acid. (0.1820 grams H2C2O4. Question? There is a reason I put the 0 behind the 2. Significant figures. Our starting numbers both have 4 significant figures. We're only doing multiplication and division, so it's the fewest number of significant figures, which would be 4. Question?
So the bottom equation, can you tell me the order of how you put that in your calculator?
It doesn't matter.
So do you just multiply straight across the top? Or do you take that first number and divide it by 2 and then multiply it by 9?
It doesn't matter.
No, I'm asking, like, I genuinely don't know how to solve that.
You multiply the things that are on the top, and then divide by the things that are on the bottom. You can do that in any order. Multiplication and division, you can switch up the order however you like.
So on the top we just multiply by 1, but on the bottom we divide by 2.
So what I put into my calculator was this number of moles multiplied by this grams per mole, because I had it in my calculator already, then divided by 2. If you did this number of moles divided by 2 and then multiplied by this, as long as you don't use parentheses, you'll get the same answer. Other questions? Okay. Now we're getting to the part that I alluded to last time, but we didn't quite get to, of course. So there's some properties of solutions called colligative properties. The co part, like together, and ligate is like another way of saying like binding or tying things together. So together, when things are mixed in solution together, these are properties that are caused by those interactions between the solute particles. Colligative properties are interesting, sort of, because they depend on the number of dissolved particles and not on the type. It doesn't matter what the type of solute particle is, just how many you have. The place that we often see this is when you add a non-volatile solute, like ethylene or propylene glycol, to a liquid like water. That extends the temperature range over which the liquid remains a liquid. Does anyone know what ethylene glycol is? Where it can be found? Coolant. Antifreeze is a mixture of ethylene glycol and water. It has properties of freezing point and boiling point that are better than ethylene glycol by itself and water by itself. The mixture is actually better. So you can buy just like neat, unmixed ethylene or propylene glycol antifreeze at like O'Reilly or AutoZone, wherever you buy your car stuff. Or you can buy it pre-mixed, ethylene glycol and water. If you're cool mixing it yourself, great, you can save some money because you're not paying for the water. Or you can buy it pre-mixed and not have to worry about that. If you just use one or the other, you won't get as good of thermal properties for your coolant. So your radiator might boil over or it might freeze if it gets below freezing. The two colligative properties that we're going to talk about are freezing point depression, which is not just being cold, sad when it's cold, and boiling point elevation. They're very, very, very similar in terms of their equations, as we'll see. Another place that we sometimes see this is salting the road, which we don't really get here very much because it doesn't snow. But if you go up into the mountains or if you go back east, oftentimes they'll salt the road because that lowers the freezing or lowers the melting point, also the freezing point, and makes it so that the road isn't as icy. Or you can just add sand to the top. If you add ethylene glycol to water, that raises the boiling point, lowers the freezing point, that's antifreeze. So for freezing point depression and boiling point elevation, the concentration is usually expressed in this unit. What's the symbol for that unit? M.
Little m.
Specifically lowercase, minuscule m. It has to be little m. If you write big M, that's a different thing. What's big M? Molarity. And this is not molarity, this is a different thing. And we really just use this for freezing point depression and boiling point elevation. It's the number of moles of solute, so that's the same as for big M, but it's per kilogram of solvent, not liters of solution, right, like we have for big M. The solvent being the liquid, usually water. Or the majority component. So molality, as this is called, is, again, with kilograms of solvent, our majority component, not with liters of solution or kilograms of solution. It's just for the solvent. We don't care about the mass or the volume of the solute. We only care about the moles of the solute. Let's do a calculation for molality. We want to calculate the molality, lowercase m, of a fructose solution containing 50.4 grams of fructose and that many kilograms of water, conveniently expressed in kilograms so that we can just plug it right into our equation. So lowercase m equals moles, in this case fructose, over kilograms, in this case water is our solvent. We have kilograms of water. We do not have moles of fructose. We get to calculate that. Fortunately, we're experts, hopefully, at calculating moles. So we'll just real quick calculate our molarity for fructose. It's about 180. So the moles of fructose, 0.279 ... because there's other stuff after that. Moles fructose. And then we plug it in. So lowercase m molality equals 0.279 ... moles fructose over 0.332 kg H2O, water. So the units that come out, 0.843 moles per kilogram. Moles per kilogram we can also express as lowercase m. So this is a 0.843 lowercase m fructose solution. Questions about those calculations? Hopefully feels pretty straightforward, pretty simple. So with capital M, that's molarity. And we pronounced it how? Molar. We dropped the itty. For molality, lowercase m, we do the same thing. So say it with me, that would be molal. So this is a 0.843 molal solution. Doesn't that sound awful? Go ahead, try it. Molal. Doesn't that feel terrible? Don't you just hate the way that feels, mush mouth? Anyway, that's why I don't like molality, because I don't like saying that. They're also very similar in terms of like the way that they're spelled. So make sure that you're careful about reading and don't get them confused. All right, freezing point expression. We have this relatively simple equation. The change in temperature I'll go ahead and write out temperature. the change in temperature, where F is freezing, is equal to the molality times the freezing point constant. K is often used to stand for constant, and the little f lets us know that this is for freezing. Kf values are different depending on the solvent. The delta T sub F, the freezing point depression, that's how much our temperature changes from the freezing point in degrees Celsius. All right, freezing point depression calculation. Delta T sub F equals lowercase m times big K sub F. That's our equation for freezing point depression. We want to calculate the freezing point of an aqueous 1.42 molal sucrose solution. We are given the Kf for water. It's 1.86 degrees Celsius kilogram solvent per mole solute, which looks kind of like crazy units. What is moles solute over kilogram solvent? Molality. So secretly, this has, it's not really secretly, it's like kind of an open secret. This has units of degrees Celsius per mole. That's all that is. So if we're multiplying something that's got units of degrees Celsius per mole times whatever mole concentration solution, then we'll just get degrees Celsius out. So all we do is plug in. We take 1.42 molal, multiply it by 1.86 degrees Celsius per molal. The moles disappear. And we get not 1, 2.64 degrees Celsius. Questions? Is that our answer? Think about what the freezing point of water is. Think about the title of the slide. What might be missing? Water normally freezes at 0 degrees Celsius. The title of the slide. Freezing point depression. What does depression mean? Yeah, being sad. Or going down or decreasing. Would it make sense for our freezing point to increase? No. What we calculated was the delta TF, the change in the freezing point, basically. So that means our freezing point changed by 2.64%, not percent, degrees Celsius. and it should have gone down. So our answer is actually minus 2.64 degrees Celsius. Questions? So the calculation part is simple, remembering to change your freezing point to make it negative because it's freezing point depression. That's the tricky part. Hopefully you all know what déjà vu is. If you don't, you'll find out soon. So the boiling point of a solution containing a non-volatile solute, like ethylene glycol, is higher than the boiling point of the pure solvent. It's also higher than the boiling point of that non-volatile solute, whatever it is. So antifreeze helps keep your engine from boiling over when it's hot during the summer, and it can't cool down as effectively. Here's our déjà vu. We just saw this slide a couple slides ago. We just changed it from freezing point depression to boiling point elevation, and we just swapped out our F's with B's. It's the same equation. B for boiling point elevation. Otherwise, it's basically the same. We are using a different constant, though, and so you have to have a value for that constant. All right. Boiling point elevation. What is the concentration in molality of an aqueous sodium chloride solution with a boiling point of 101.78 degrees Celsius? For water, Kb equals 0.512 degrees Celsius per mole. This is a harder question than the freezing point depression one. Delta T sub B equals lowercase m times Kb. What are we being asked to find in that equation? Concentration, which is which of those three terms? M, lowercase m. The concentration in molality. So if we want to find m, we need to get m by itself. Divide both sides by Kb to get it to disappear from the right side. If we flip it left to right, m equals delta Tb over Kb. I'll let you do the calculation, and then we can compare. Anyone have a number for me for the concentration? Yeah.
198.63.
198.63. You've activated my trap card. Thank you for your bravery. All right. You might have gotten, I'll show you one version. Let's do it in red. If we put in 101.78 degrees Celsius over 0.512 degrees Celsius per mole, I'm condensing the units. That'll give us a staggering 198.79 molal sodium chloride in water. That means that we have 198.79 moles of sodium chloride in 1 kilogram of water. If we calculated out the grams of that, which I did because I thought it would be funny, it's 11,619 grams of salt in 1 kilogram, 1 liter of water. Do you think that you can fit 12 kilograms of salt in 1 liter of water? Like an Nalgene bottle? Probably not, right? So that would be one way of figuring out that we did things wrong. That's levels of salt you'll only find in a Call of Duty lobby. If you're playing with me and my friends. It's my friends, not me. So what was the mistake that we made? What did I plug this 101.78 in for? What was that term? Delta TB. So delta is key. This is the change in boiling point. That's how much our boiling point went up, our boiling point elevation. What's our normal boiling point of water? 100 C. So our change is 101.78 Celsius minus 101 or 100 degrees Celsius for 1.78 degrees Celsius. If we plug that number in, we get a much more reasonable number, 3.48 molal. That's 200 grams of sodium chloride per kilogram liter of water. You don't need to have done that last part. I'm just doing that because I want to talk about something. Questions about the calculation? Again, the tricky part is the delta. The triangle is the tricky part. How many of you have made pasta, like just cooked pasta, not like do the dough and, right? Okay. Not as many people as I would hope. It's not that hard, guys. Give it a try sometime. You may know that you're supposed to add salt to your water, your pasta water, when you cook it. Why? Flavor? There's another explanation that I've heard as well. It doesn't affect sticking. But you might have heard that. If you want it to not stick together, you add oil, but then that makes the sauce not stick to it either. Another reason that I've heard people say is that if you add salt, just a pinch of salt somehow magically going to raise your boiling point, your pasta will cook a little faster. Our boiling point here changed by 1.78 degrees Celsius. We added 200 grams for 1 liter of water. That's a lot more than a pinch. And you're probably using at least 4 liters, so we would need like almost a kilogram of salt to get a little 2 degrees Celsius boiling point change. It's not going to affect the boiling point. If you just added a pinch, a dash of salt, it doesn't do anything for your boiling point. So if you've heard it, or if somebody tells you that, you can say, no, I learned about this in school. And they'll be like, you learned about this in school? Yeah, I learned about this in school. My professor's crazy. So there's another fun aside. Last thing we're going to talk about for this chapter is osmosis, not Jones. Osmosis is the flow of solvent from a less concentrated solution so like more pure water to a more concentrated solution. Has more stuff in it. So what's happening is, in osmosis, you've got a membrane, and water can pass through the membrane. Your solids, your dissolved particles cannot pass through the membrane. They're stuck on their sides. One of the sides has more concentration, more solute. The water, because it can freely flow through, will flow through and kind of get stuck with the stuff, the colligative properties stuff. And so it ends up flowing to the more concentrated side until it's an even concentration. We'll see some pictures. So this is what an osmosis cell might look like. We've got a semi-permeable membrane. Only the water can flow through the membrane. We've got a 1 molar solution and a 0.1 molar solution. The water from the lower concentration side flows through to the higher concentration side, and that results in a change in the amount of water on the one side. And we get this value of table. And you can calculate things about the solution from that table value. It's actually pi. And we would call it the osmotic pressure of the solution. That's also a colligative property. It only depends on concentration. The more concentrated the solution, the greater its osmotic pressure. So this water on the right side would get higher if it had started off at a higher concentration. And this is important for our bodies because our cells have membranes that are semi-permeable membranes. Water can move through them pretty easily. Ions and other things can also pass through. But if you put them into seawater, for example, seawater is really salty. And so the water from your cells, or the cells that we put in the seawater, will flow out, and that'll dehydrate the cell. They get all like virus looking. They're all pointy and pokey. The opposite is also true if you put it into a lower concentration solution. Here we have pictures. If you put it into a lower concentration solution, water is going to flow into the cell, and that can cause it to swell up or even pop. I don't usually ask questions about osmosis. So we've got 3 words related to osmosis. Isotonic, tonic just meaning like the concentration. So iso meaning it's the same. Isotonic solution is the same concentration. The solution concentration is the same. Hypotonic, like hypodermic needle or hypochlorite, less than. The surrounding fluid is lower in concentration. We also have hypertonic, where the surrounding fluid is more concentrated or a higher concentration. Osmosis is kind of cool because, moving water, you've also probably heard of reverse osmosis water filtration. So reverse osmosis water filtration uses this idea. It takes a semi-permeable membrane and you just apply pressure to whatever the solution is, and it'll force the water to go through the membrane. So it's like the opposite process of what's going on here. That's why it's called reverse osmosis. So you're forcing water through a membrane. The membrane catches everything that's not water. You might do a couple of rounds of that. And that's how reverse osmosis water filtration works, in a nutshell. If you're not in a nutshell, it doesn't work that way. Questions? Okay, that will do it for this chapter.